What you're looking at is not just a jet engine. It's one of the most advanced turbofan engines ever built. This is the LEAP 1A, the powerhouse behind the Airbus A320neo. And it's designed to push the limits of efficiency, power, and engineering. But how powerful is it really? How hot does it get inside? And why does most of its thrust come from air that never even enters the core? In this video, we'll examine the amazing engineering of turbofan engines. Let's break it down. The LEAP 1A is manufactured by CFM International and is one of the most widely used engines in modern aviation. It powers the Airbus A320neo family, one of the most popular commercial aircraft in the world. And at first glance, it might look like just a big spinning fan. But inside, it's an extreme environment of pressure, temperature, and precision engineering. Let's start with the physical scale. Fan diameter, nearly 1.98 meters. Engine length, about 3.1 meters. Total weight, roughly 3,000 kilograms. That's about the size of a small car hanging under a wing. And that massive front fan? It's the key to everything. The turbofan engine produces between 24,000 to 35,000 pounds of thrust. That's enough to push a fully loaded passenger aircraft down the runway and into the sky. But here's the surprising part. Up to 80% of that thrust comes from the fan, not the core engine. This is what makes it a high bypass turbofan. How it works. Air enters the engine and splits into two paths. Bypass flow, majority. Flows around the core. Generates most of the thrust. Core flow, minority. Enters the compressor. Gets compressed, burned, and accelerated. Inside the core. 3-stage low-pressure compressor. 10-stage high-pressure compressor. Annular combustion chamber. High and low-pressure turbines. Each stage increases pressure, extracts energy, and keeps the engine running. Now here's where things get extreme. Compressor exit, 400 to 700 degrees Celsius. Combustion chamber, 1500 degrees C. Turbine inlet, 1400 degrees C. That's hotter than molten lava. And yet, the turbine blades don't melt. Why? Because they are made from advanced superalloys and are cooled internally with air channels, a masterpiece of engineering. Let's talk about speed. Fan rotation, 3000 RPM. High-pressure turbine can exceed 10,000 revolutions per minute. At these speeds, even the slightest imbalance would destroy the engine. So everything must be perfectly engineered and balanced. Fuel efficiency. Compared to older engines like the CFM56, the LEAP 1A offers 15% lower fuel consumption, lower emissions, reduced noise. It achieves this through advanced composite fan blades, higher bypass ratio, 12:1, improved aerodynamics, 3D woven carbon fiber materials. Interesting facts. Here are some facts that might surprise you. The fan blades are made of carbon fiber composite, not metal. Each blade is incredibly strong, yet lightweight. The engine operates in temperatures close to material limits. Most of the air never touches combustion, it simply gets accelerated. The engine must survive bird strikes, extreme weather, and massive stress cycles. Now let's get to the most mind-blowing part. To truly understand the power of this engine, we need to look at real-world numbers. This engine is not just powerful. It also consumes an incredible amount of fuel. For example, even at idle, the engine burns around 600 to 800 kilograms of fuel per hour. But the real shock comes during takeoff. At full power, a single engine can consume up to 3,000 kilograms of fuel per hour. Do you know what that means? That's almost 1 liter of fuel every second. And don't forget, this aircraft has 2 engines. So where does all this fuel come from? An Airbus A320neo can carry approximately 26,000 liters of fuel. That's equivalent to about 400 full car fuel tanks. Now here's another insane number. The speed of the exhaust gases leaving the engine. Around 1,500 to 2,000 kilometers per hour. That's faster than the cruising speed of many aircraft. And yet, here's the surprising part. This high-speed exhaust only produces a small portion of the total thrust. Most of the thrust still comes from the fan. With every takeoff, 1,500 degrees Celsius temperature. Speeds exceeding 10,000 revolutions per minute. Immense pressures. And yet, it can operate under the wing for more than 10 years. And during that time, it makes thousands of takeoffs. It endures extreme heat and stress. But it still has to remain safe. That's magnificent engineering. These beasts, consuming tens of liters of fuel per second, play a role in transporting thousands of people to distant cities today. And humanity has pushed the boundaries of engineering to reach this level. The turbofan engine is not just an engine. It's a perfect balance of physics, materials science, and engineering precision. And next time you see an Airbus A320neo take off, you'll know exactly what's happening inside. If you enjoy deep dives into engineering like this, don't forget to subscribe to channel. Because this is just the beginning. See you next engineering video.